Hello everyone. Today we are going to discuss on our research topic, that is AI assisted data organization framework for distributed multi-cloud storage systems. I am Shreyas and I have performed this task along with my teammate Pratik. In this presentation, we will discuss the problem in current multi-cloud systems, give our AI based solution, discuss the methodology, the machine learning approach, the results and the future scope. So let us begin. So this is the content that we will be discussing throughout the video. Our topic, that is AI assisted data organization framework for distributed multi-cloud storage systems. Uh, in today's digital world, huge amount of data are generated every seconds through social media platforms, cloud applications, online transactions, IoT devices, and business operations. To manage this amount of data, companies use distributed multi-cloud system storage, where data is stored across different cloud providers like AWS, Azure, and Google Cloud. These systems provide better scalability, reliability, availability, and backup support. However, traditional storage systems mainly use static storage methods and fixed rules. They cannot intelligently analyze changing data access behavior. For example, frequently accessed data may remain in slower storage, while less important data may occupy high performance storage. This reduces efficiency and increases operational cost. So our project proposes an AI-based framework that can automatically organize, classify, and optimize data storage across multiple cloud environments using machine learning techniques. Now the problem statement. The major problem in distributed multi-cloud storage is inefficient data organization and management. Now the existing systems have increased storage cost, increased increased retrieval latency, use static rule-based methods, and they do not dynamically identify hot and cold data. Hot data refers to frequently accessed data, while cold data refers to rarely accessed data. Since traditional systems cannot fully adapt dynamically, storage resources are not utilized efficiently. This leads to performance degradation, high maintenance cost, slow data access, and poor storage optimization. Another challenge is that manual monitoring becomes difficult as cloud data continuously grows. Therefore, our proposed systems uses machine learning techniques to intelligently classify data and automate storage management decisions. The motivation behind. We were motivated by a rapid growth of cloud computing and large scale data generation. Modern organizations require faster data retrieval, better storage optimization, reduced operational cost, and automated decision making systems. Today, businesses handle terabytes and petabytes of data daily, which is a huge amount. Traditional systems are static and depend on predefined configurations. They cannot learn from changing usage patterns or dynamically reorganize storage. For example, if access frequency changes suddenly, traditional systems fail to adapt efficiently, which is a huge problem. So, taking this problem into consideration, this inspired us to design an intelligent AI driven framework that can learn from data behaviors, that can predict storage requirements, and automatically optimize cloud storage allocation. So, basically, our goal is to make multi cloud storage systems smarter, faster, and more efficient. Now, the research objectives of our topic. The research objectives of our work are: first, to develop an intelligent data organization framework for distributed multi-cloud environments. Second is to classify hot and cold data using machine learning algorithms based on access behavior and system parameters. Third is to optimize storage placement by considering performance, cost, and resource utilization. The fourth objective is to enable automatic data migration whenever access patterns change dynamically. Fifth, to improve overall storage efficiency and to reduce retrieval latency. And finally, to design a scalable and adaptive system that can work efficiently in modern cloud infrastructures. These were the objectives that we took into consideration. Now, the next part is the literature review. So, here we have studied various existing research papers that are mainly related to multi-cloud storage systems, data placement strategies, cloud storage and optimization techniques, AI and machine learning in storage systems. So, several researchers propose methods for load balancing, data replication, storage optimization, and metadata management. Some systems improved performance and scalability, while others focused on reducing storage cost. However, most existing systems focus only on placement or optimization individually. Very few systems provide intelligent automated organizations using adaptive machine learning techniques. What we have observed is that many traditional systems rely heavily on manual configurations and also static thresholds. So this was one of the research gap that we found, and this research gap motivated us to develop a more intelligent and automated AI assisted framework. Now the research gap. The main research gap identified from the previous studies that were the literature review that we discussed in the previous section uh, is that most existing systems rely on static and rule-based techniques. These systems cannot adapt dynamically and they lack intelligent learning capability. They require manual intervention. They do not efficiently support real-time automation. So very few systems use adaptive machine learning for dynamic data organization in distributed multi-cloud environments. Another important gap is the absence of automatic migration based on real-time access behavior. So most existing approaches also fail to combine intelligent classification, continuous monitoring, dynamic optimization, and automated migration. So therefore, there is a strong need for a smart AI assisted framework that can continuously learn and optimize storage decisions automatically. Now the proposed methodology. Uh, Here we can see from we go from start, then ingestion, then feature extraction, then pre-processing, then classification, which uses random forest, then decision engine, and then storage allocation. After the second phase would be uh, access request, metadata, retrieval, monitoring, and updation. And the migration decision would be based on if migration is required, yes, then migration, then metadata update. If no, then the data is retained. The Now I will explain in detail. The first stage is data ingestion, where workload and storage related information is collected from cloud environment. The second stage is feature extraction, where important parameters are identified. These important parameters include CPU usage, memory usage, access frequency, throughput, and latency. The third stage is pre-processing, where missing values are removed, data is normalized, and labels are generated. After pre-processing, we perform classification, which uses random forest machine learning algorithms. The classifier categorizes data into hot data or cold data. So based on these results, storage allocation uh, engine determines the most suitable storage location. Finally, the monitoring system continuously tracks behavior and automatically migrates data whenever required. Then the migration decision happens, where if migration is required, then metadata is updated. If no, then it is retained. Now here you can see the flow chart of our idea. So basically here we go from start, then data ingestion, then feature extraction, then pre-processing, then machine learning classification that uses random forest, then prediction and processing, then decision engine, and then storage allocation, then data storage, then metadata management, then user access handling. Access handling has a convergence, that is if pattern change, if yes, then data is migrated, metadata is updated, and then system is updated, and then monitoring happens. If no, then the state is maintained. This was the clear flowchart that we have used in our topic or idea. So this flowchart represents the complete workflow of the process system. The process begins with data collection from distributed cloud environments. Then the data moves to pre-processing and feature extraction stages. After pre-processing, the machine learning classifier that in our idea we have used random forest. It uses a classifier that classifies and analyzes patterns across our system. So based on the classification results, frequently accessed hot data is stored in high performance storage, and rarely accessed cold data is shifted to low cost storage. The decision engine continuously monitors system behavior. If access patterns change over time, automatic migration is triggered to maintain optimization. This workflow helps to improve efficiency, speed, scalability, and resource utilization. Now, I would like to tell you about our dataset. The dataset contains workload and storage related parameters collected from multi-cloud environments. The dataset includes features such as CPU usage, memory usage, disk I/O, network I/O, network throughput, latency, cost, and resource utilization. These parameters helps the machine learning model to understand storage access behavior. For example, frequently accessed data generally shows higher CPU and memory usage, and rarely accessed data consumes fewer resources. So this data set simulates realistic cloud workloads and supports efficient training of machine learning models. Uh, Taking these all features into consideration, our system can intelligently classify data and improve storage allocation decisions, which is uh, the crux of our topic. Now the dataset pre-processing. The dataset pre-processing steps include, uh, sorry, before training the model, pre-processing is performed to improve data quality and accuracy. So in our dataset, the pre-processing includes steps like missing values are removed, duplicate entries are cleaned, features are normalized, irrelevant data is filtered. So we also have made an estimation of access frequency, utilization patterns, and resource consumption. After cleaning the dataset, labels are generated for hot data and cold data separately. Then proper pre-processing is very important because machine learning performs better on better data quality. So this stage basically improves accuracy, reliability, and prediction performance. Now, this section contains the dataset features graph. Here you can see utilization, cost, throughput, latency, price per hour, RAM, CPU, VM type, region, cloud provider, disk I/O, net I/O, memory usage, and CPU usage. And we have scaled it on a scale of importance score. So this graph basically shows the feature importance used by machine learning model. The graph helps us to understand which parameters contribute most to classification. The CPU usage and memory usage have the highest importance because frequently accessed data consumes more system resources. The disk I/O and throughput also play significant roles in identifying active workloads. The latency and cost helps to optimize storage placement decisions. And the so in conclusion, feature importance analysis improves model interpretability and helps identify most influential parameters affecting storage behavior.
So now let's talk about classification graph. This graph illustrates the overall distribution of data across the three classification categories such as hot, cold and no action. Hot data has the highest percentage because active files are accessed more frequently as compared to cold files in the cloud environments. Cold data represents the files that are rarely used in the system. So the proposed approach for our research title would be as stated as our proposed system uses a supervised machine learning approach. We selected the Random Forest Classifier because it provides high accuracy, handles large data set efficiently, reduces overfitting, and input features are pre-processed and transformed before training. The system incorporates real-time access monitoring and also maintains the metadata for adaptive behavior. And the system also proposes an automatic data migration which is triggered based on access thresholds and classification outcomes. This framework also includes real-time monitoring with metadata tracking and automatic migration. The trained model predicts whether the data is hot or cold, and accordingly it is classified and stored. The evaluation metrics for our research title would be stated as follows. To evaluate the system performance, we used several matrices. First is prediction storage accuracy, which would be calculated as correct storage decision divided by total scenarios, which eventually measures how correctly model predictions, that is hot or cold, is translated into actual storage placement points. The next would be hot data placement efficiency, which would be evaluated as hot data in high performance storage divided by total hot data, which ensures frequently accessed data is stored in high performance systems. The next evaluation matrix would be as cold data cost efficiency. Cold data in low cost storage divided by total cold data would give us the following matrix, which evaluates effectiveness of cost reduction through optimal placement. And the final evaluation matrix would be as migration effectiveness, which would be calculated as successful migrations divided by total migrations, which evaluates whether data is migrated and improves the system performance. Now let's talk about the result and analysis which we have done on this following topic. So our model achieved approximately 85 to 90% of accuracy. The confusion matrix shows strong classification with minimal prediction errors, and the confusion matrix data is as stated on the screen. First of all is actual hot data and the predicted hot data, which is 420. Actual hot data and predicted cold data would be 30. Actual cold data with predicted hot data would be 45, and actual cold data with predicted cold data would be 405. The system successfully improved storage efficiency. It also reduced retrieval latency. Along with it, the system optimized storage allocation. The balanced dataset also helped to improve model generalization. Along with it, we have shown a model performance distributed graph. The green bar shows the correct prediction, whereas the red bar shows the incorrect predictions. Now let's talk about another graphical analysis. The graphical analysis of this model compares actual and predicted classifications, which are shown as the blue bar shows the actual predictions, whereas the orange bar shows the predicted values. The predicted values closely match the actual values, showing that the model learned the data patterns effectively. This demonstrates the reliability of the proposed framework. Balanced training and strong feature relationship allows our model to learn and generalize effectively. Now, talking about the future scope of this research topic would be that in future this system can be improved further by, first of all, is self-learning AI models, uh, along with it predictive data placement and real-time pricing optimization, geographic awareness storage optimization. This framework can also be integrated with advanced cloud security mechanism to provide intruder attacks. We can also incorporate the user behavior modeling to enable personalized and adaptive storage decisions. We can also integrate a real-time cost optimization mechanism, which would be dynamic in price-based models. So to conclude, our project presents an AI-assisted framework for efficient multi-cloud organization. Using machine learning, the system intelligently classifies data and automates storage decisions. The framework improves, first of all, is performance, cost efficiency, and storage management for corporate resources. Thus, we can say that AI can significantly enhance distributed cloud storage systems by integrating intelligent predictions, dynamic access tracking, and automatic data migrations. Thank you. We hope you find our project informative and interesting.